So like Isaac said, I'll be talking to you about learning quantum data structures from classical noise. And without further ado, let's get into it. Okay, so brief outline. First, we'll discuss the goal of what we're doing. I'll present the not too complicated algorithm that accomplishes that goal. We'll look at some early results and then discuss a simple use case for this, okay? So what we want to do is to take discrete samples from what might be called a hard data distribution and use them to learn the underlying fundamental distribution. So a hard distribution might be something that's sparse or multidimensional or otherwise just difficult to capture in a small number of samples. What we're going to do is have a quantum circuit that we use as a learner that's actually able to do this capturing more efficiently than it would be without it, right? Okay, so basics of the algorithm. We're going to have two steps here. They're going to be training and generation. And in the training step, we're going to take a handful of points from the hard distribution, and we are going to embed them in the Hilbert space. And then we're going to learn the process that evolves these embedded points into an easy points from an easy distribution. So what's easy may be like Gaussian noise or something like that. So very simple to understand, very simple to capture and quantify. That will be the training step. And then the generation step will essentially do this backwards. So we'll embed easy states and use the circuit with the optimal parameters to transform them into points that are representative of the difficult distribution. If this sounds familiar to you at all, this is sort of pretty typical of a diffusion network kind of setup in classical machine learning. And at the bottom here, I have sort of a visual representation of what that might look like. Now, my hard data here, you can see my mouse, yes. So the hard data here is just an S-curve data set. It's not actually difficult, but just for the purposes of the demonstration, that's what we'll use. And my easy data is just Gaussian noise. And what will happen is the training step will run from right to left here. So we'll sample points from the hard distribution, and we'll slowly transform them into noise. And then the generation step will go left to right, taking the noise back into the hard distribution. So if we want to look at this a little bit more technically, we can think of having a state that's representative of the noise data embedded in Hilbert space, and we are learning a transformation that can take that state into a state that's representative of the difficult data also in Hilbert space. And breaking that down, so we can actually do this with arbitrary complexity. So we can think about having however many time evolution steps that little by little transition one data point into the other. Or we can actually just fold this trivially and just try to do it in a single step. It's rather open-ended, exactly how you want to implement this. So here's an example of like the minimal version. And I have on the right just some PennyLane code that will implement the learner circuit in this case. Now, I hope this looks familiar to everyone. There's nothing too crazy happening here at all. I have a simple projector matrix, and I'm defining a Q node over here with some device. And then the actual embedding that happens, I'm just going to use the QAOA embedding template to do this. Now, you'll note there's actually no explicit time evolution happening here. And like I said, this is the minimal version of the algorithm. We're just going to pretend that there's one step, and we can take the noise data to the difficult, important data just by learning a single evolution step. So one thing about this circuit is that you can see it actually grows exponentially in size. Not the circuit, sorry, the projector that the circuit uses grows exponentially. So this is okay if we have, say, 2 to 10 wires, but it's going to take up a lot of memory if this projector becomes, billions of units wide. So you can actually do a swap test circuit to do the same thing if you want to do it more memory efficiently, but this is going to work for us. Here's a slightly more pictorial representation of the same idea. There are 3 learnable parameters in this case. So that's going to be parameters for the data space embedding, parameters for the noise space embedding, as well as the Hamiltonian process. Now, the third thing I have neglected for the purposes of this example. But as far as the first 2, if I just go back to my circuit here, you can see that over here, I have 2 sets of parameters, namely alpha 1 and alpha 2, and then I have my data and my noise here. This looks a lot like a kernel circuit, if anyone here is familiar with that, but strictly speaking, it is not a kernel circuit because these parameters are, in general, different, alpha 1 and alpha 2. And what we're looking at conceptually is that we have a Hilbert space that's determined by our circuit. And we're going to embed the 2 points there, and we're going to work entirely in Hilbert space to try to turn one into the other. And in the end, we have something that can take just very easy to sample data, even a single data point, and via the transformation recover a distribution that's representative of the more complex data. And what points in that distribution will look like is there'll be a weighted superposition of the data points that we sampled with the weights determined by the noise points that we put in. Okay. Now, let's look at some early results. And before I do that, just a quick plug for Covalent. So Covalent is a workflow orchestration platform. It lets you design complex workflows, run them in the cloud. If you don't have the compute on your laptop, it's super easy to use and Pythonic. Covalent Cloud is the paid version of that adds enterprise features and sharing and better hardware availability as well. I'll have a link at the end if anyone's curious to check that out. And what I have on this next slide is the Covalent workflow that generated the results that I'm going to show you shortly. So what you're seeing right now is a directed acyclic graph, which is just a fancy way of saying a kind of like a process made of a bunch of different nodes that goes from top to bottom in this case. And what's happening here is I'm running a workflow that does the training and generation process for 3 different data sets. And one of these will be the S-curve that we saw earlier. And then I believe I have a circles data set and a moons data set. These are sort of just standard data sets from scikit-learn. Maybe lots of them will be familiar to you. And yeah, so that's reflected in the shape of the transport graph that we're seeing here. You can see distinctly we have 3 different branches over here. What's cool about this is that the code for this is just a for loop over the 3 data sets, and Covalent figures out that, yeah, I can actually do this in parallel. I can run the 3 branches independently, combine the results at the end, and send them back to the user. But anyways, moving on. Oh, why is my, okay. I would like my GIFs to play correctly, but unfortunately, okay, now they've all stopped. Okay, let me see if I can get this going because it's pretty cool. Well, back in. There we go. So hopefully you can see it happens rather quickly, as you can tell from the loss curve here. So most of the change happens maybe in the first fifth of the length of the GIF. But what happens is we go from a background of just complete noise. Overlaid on top of it is the original data distribution, which is to represent the hard data in this case. And what you can see is the noise in the background sort of changing density over time to match the distribution in either case. I'll play that one more time just for fun. See it come out? And indeed, what this is, what the animation is just steps in the training process outputted as images that I've combined into a GIF. And we see, indeed, in each case, it trains, the model trains. This is a very typical loss curve you see from a successful training run. What we're seeing on the bottom is a metric called the Wasserstein distance. I hope I'm pronouncing that correctly. What that is it's also known as the Earth mover distance. So that's going to be the amount of effort quantified numerically to turn one distribution into another. And the way I'm comparing these two things is I'm taking a kernel density estimation based on the real data points, and then that gives me a distribution that I can compare to the target distribution. So how do we verify that this is actually learning? Well, apart from our wonderful loss curves, we want to test that the model actually performs the way that we expect it and that it fulfills our goal. So if you remember, our goal was initially to capture a difficult to represent and difficult to sample distribution by training our circuit such that we can take points that are easy to sample, put them through our circuit, and recover the difficult distribution. And that's what we're seeing here. So here we have two figures side by side. Overlaid on top of the grayscale stuff in the back are these red data points. So these are just data points from Gaussian noise. Now, Gaussian noise is the easy data, right? So on the left, I have Gaussian noise, which I didn't use to train my model. In this case, I'm sampling some of these points over here, which are not too far from the center where the real data is. But because these points are not the ones that I trained with, you can see that the distribution that I get back is actually not the S-curve. Maybe arguably it's a little bit similar, but it's certainly not the beautiful, it's not that pretty, but the S-curve that I see on the right. So here on the right, when I sample points from a distribution that I actually used to train the model, these little red dots, even just one, I can recover the point density from the quote-unquote difficult distribution, which is the S-curve in this example. Okay, and a little bit more math. This is just our training process. And to reiterate, what I get back when I put in a noise point is a weighted superposition of the difficult points that I sampled, which gives me, lets me recover some representation of that difficult distribution simply by just putting in one point of noise. The one catch here is that the output data is only accessible as a quantum state, and tied to that are all the difficulties that come with it. Okay, that's all for me. On this last slide, I have a QR code that'll take you to the main Covalent website. We have our open source repo at agnostichq/covalent. Check it out. It's free to use. And if you do check it out, please give us a star. We would really appreciate that. We're also on socials on X, formerly known as Twitter. And yeah, you can see all that here. So I'll leave this slide up for a little bit. And that's it for me. Thanks so much.
All right. Thanks a lot, Ara. Really appreciate that. You did a really good job. Like you said at the start, bear with me here, just kind of pick this up. How long did you have to prep for this talk?
About an hour and a half while I was already doing something else. So
nice. I think that's pretty impressive. So maybe we can get some claps in the chat for Ara. That was really good. So you'll be in Discord. Will you be in Discord specifically, or will somebody else from Agnostic be in the Discord?
So my colleague Ian is in there right now.
Yep.
I will also join in a little bit.
Cool. Yeah, Ian is in the chat as well. Hi, Ian. Thanks for joining.
Santosh might be in there as well.
Okay. Sure, cool. All right. So we have a question from Dentucky Kirby. This is really interesting, but what is the purpose of learning quantum stuff from noise that is classical? It has no quantum stuff in it, so are we manifesting quantum stuff from nothing?
I wouldn't necessarily put it that way. So I think a better way to think about the goal here is that you have real data at both ends. So you have two pieces of real data, or rather real data distributions. One is easy for you to access, because you can just, it's Gaussian noise. The other is something difficult. And what we're doing is using the quantum stuff in the middle just as a way to get from the easy stuff to the hard stuff. So the hard distribution will be difficult to understand and fully capture with a few number of samples. But hopefully, when we train our quantum circuit, you can put in easy data and take a shortcut through it to the difficult data without having to manually sample the difficult data. So the goals are entirely real. The quantum bits in the middle are just to facilitate the goal. I hope
that's clear. Is there any, I guess, is there any application, or I guess, is there anything useful to extract from like the intermediate representation of the data in the classical realm, or are we like maybe that was the part of the question there that Dentucky Kirby meant?
It's difficult to think conceptually about quantum data, at least for me, but the one kernel of understandable bit here, I think, is that the quantum data will be some superposition of the actual points, the small number of points that you're able to get from the difficult data. So based on how we manipulate that superposition, we can turn it into sort of a blurry, kind of hopefully accurate version of the actual data. That's kind of the main quantum-ish thing that we're using here, is a weighted superposition of the real points, weighted in a very learned and trained way.
Right. Okay, cool. Another question from Ivana. I have to admit, I haven't used Covalent very often yet. How difficult is it actually to get started properly?
Not at all. It's totally in Python, and I suppose the one prerequisite is that you have your code arranged into a bunch of neat functions, totally normal functions. But yeah, that's about it. And then you take that, put a bunch of decorators on top, and you're good to go. We have a quick start guide on our website, covalent.xyz, which I believe the QR code will take you to. The quick start is in our docs, which is one click from the website. I would say check that out because it'll get you started right away. It's totally simple, I promise.
Cool. I'm going to leave this slide up here a bit more for people in the chat in case you want to go check the website out and scan that QR code. Okay, one more question from Catalina. Do you use PennyLane often?
Yeah. Oh, it's actually my go-to. So I've spoken with some people at IBM, and I've told them how much I like PennyLane over Qiskit. Yeah.
Nice. Okay, cool. All right. Well, if there's any more questions for Ara, please head on over to the Discord. Ara and Ian will be there to answer your questions. That's really awesome of you guys both to do that. Really appreciate it. Yeah, I think that's it for now, Ara. So we'll say goodbye and see you in the Discord.
All right. Thanks, Isaac.
All right. Cheers.